Okay, that's good. So now what I want to do is, so what we have now is we have the equation for the trajectory of a material point or a tracer in this random flow. Okay. But ultimately, I want to see what is the effect of the random flow, right, in some kind of average sense. So if I release a bunch of tracers, what happens to them? Right? And we expect the turbulence to mix things. Right? So I put tracers, so let's consider the case where there is no mean flow. Right? So the average of DUI is 0. Right? So if I just put tracers in such a flow, no mean, if there's no fluctuation, I'll just sit there. So a tracer will remain in the same position. Now because there are fluctuations, the tracer can go up, come back down, go up, come back down. What is the mean effect? Right, is the question. So if I look at just one particle, it will have no mean effect. It will on average be in the same position. But what about the mean square displacement? Right? So the mean location will not change, but if I look at mean square displacement statistically, that should spread, we would expect, right? Because we expect turbulence to mimic random motion like random walk. In other words, we'll expect some diffusion. This is the idea of eddy diffusion, right? Because we expect if you put many particles in a turbulent flow in a small circle, after some time they'll spread. In other words, turbulence should mix. Right? So can we obtain this result now from what we have, right? So right now we have an SDE for one particle's position. So what we would like to do is look at the evolution equation for a distribution, probability distribution of this particle. That's the equivalent of saying concentration, right? If I have a dilute system. So let's do that now because we know exactly how to go from a SDE to the Fokker-Planck. So let's look at the Fokker-Planck equation for a particle in this Kraichner flow and see what it looks like. And does it give us some sense of diffusion? Yes. Yeah, so I'm looking at the PDF. Right, so I have some trajectory, that's my particle, which is varying in time, and I want to know what is its probability distribution function, right? Assuming that I start from some location. That's a classic Fokker-Planck equation that I want to derive from my SD, right? So we'll do the same thing we did to go from SD to Fokker-Planck in our earlier part of the course, right? What we will do is we look at the evolution of some expectation of some function f, right? So for some function f of x, I look for how the expectation evolves, right? And I'm going to say that this is the same as df by dt. That means integral. So this, of course, I can take the dt inside. I'll have f is not dependent on time. So I'll have dp dt, partial derivative. And dv is the integral over the volume, because p is defined over xyz. So to find the average position, I would take the PDF, integrate the PDF over the volume. So dv is just integral over the volume. So this just follows from this definition, right? So I take ddt of integral fp dv and take the dt inside. And here I have to find 1 by dt times df. So now what is df? I will, to take the mean of df, I have to find df equation, right? And that I can find the equation for the increment of f of x from the equation for dx using Ito's calculus, right? Okay, now I have an Ito equation. So that was the reason of going from Stratonovich to Ito, right? So I started with the trajectory equation, which was Stratonovich. I've shown that the Ito version is identical in compressible flow. So now I can use Ito's calculus to find equation for f, right? So I know that dx again is equal to dui. Dxi is dui, right? It's the Ito. So now I want f of x, right? So along the trajectory capital X, how does f change? This is what I want to know. So remember what that will be. It will be dou f by dou x I dxi plus I have to go to the higher order, right? Because I am doing Ito's rule. Okay, so if I substitute now, dxi is just the same as sorry, dxi dx. Correct? So I mean, this is the Ito's calculus, right? You take, it's a chain rule, but you have to go to the second order because remember, the du's are like root dt, right? So this is my second order term. And now again, this I have to replace by its mean square limit, which is the correlation, right? So it's the average of these things. So this term then becomes right? Remember, this is again at the same point, no? So delta ij d at 0, which is just the variance of the velocity. So ultimately, I'll get so now I have my equation for df. Right, so df is basically dou by dou xi dui plus this stuff. Okay, so these two terms are there. And now I substitute in here with the average. Okay, so if the average of dui is 0, it will go off, but we don't have to do that. Let us keep it. So now I'm going to have integral of f dou p dou t dv is equal to, on the other side, there's dt here, right? Because this is delta ij, etc. dt. Okay, so this formula for df, I have to take the average. Correct? So when I take the average, if I take the average of this, df by dxi comes out, I'll get the average of dui. If it is 0, this term will knock off. If it is not, it will stay there and get divided by dt. So this is nothing but the mean velocity. Right? Since this average is a constant and it will go like dt, I can write it that way. So that's just for interpretation. Okay. Or another way of just saying it is, I can set this to 0. So I can rewrite my velocity field as a deterministic drift part plus the Krykman model. Okay, so if I do that, then this is like the deterministic part of the velocity. And this is the interesting stuff. This is the stuff having to do with the correlation of the velocity. Okay. So I could set this to 0 if there is no mean. So now what's going to happen? So if it exists, what I can do is, in this term, I can multiply this term by integral p dv. Right? Because integral p dv is 1 by definition of the PDF. So I can introduce integral p dv just to get it in this form. And now you will see, right? I look at the two sides, you know what to do. Do integration by parts and flip the dx onto p, which we have done multiple times. So right, and take homogeneous boundary conditions on f of x, right? Just like we did in our derivation. So f is some arbitrary function, I can make it 0 at the boundaries. That will knock off my boundary terms after I do integration by parts. So finally, just like we did in our previous derivation, you will take f out and you will get derivatives on p. And you can see that this thing will give me a drift. I mean, it will give me a advection term, so that I get dou p by dou t for the PDF of the particle is equal to minus the mean velocity stuff, which is the standard advection term, right? Plus, this is the interesting thing. So this would be 0 if I take a 0 mean velocity, right? But the interesting thing that's coming now is I'm going to get the variance of the velocity field, or the, right, by 2 the function f to be homogeneous at the boundaries. So you knock off the boundary terms. That's exactly what we had done right earlier when we derived the Fokker-Planck from the SD. Right, and you see now the form of this equation. Sorry, this is not f, this is p. Okay, so finally you get a Fokker-Planck equation like this, right? And now what is this? You see you have a diffusion term. So in other words, if I start with a Dirac delta PDF, that means all particles are located at a certain point. How will the PDF evolve? It will evolve according to a advection diffusion equation. So if you have mean velocity, all the particles will move. And if you have, and because I have the variance of the velocity, which I have specified, right? Variance of the displacement field, that will create a diffusion, right? In classic physical diffusion form. Right? So the PDF will evolve with constant space-independent diffusion. And this is nothing but the Eddy diffusion. So d0 by 2 is Eddy diffusivity. So now this is the remarkable result that we were thinking about from the beginning. Right? So what we have shown is you have a turbulent flow, or you have a random flow field, right, which you are using to mimic turbulence. If I look at particles in this flow field, they will behave like they're diffusing. Right? And we have just proved that exactly. And that diffusion coefficient effective will be given by the variance of the velocity field by 2. It's not exactly variance of the velocity field, right? It's so d, remember, is the variance divided by dt. Okay, depending on, because of how we specified the Crichton flow field. Basically, it's a second moment. So it's related to the variance of this displacement field that you're creating, the variance of the noisy field. So that directly gives you the Eddy diffusivity coefficient or diffusion coefficient. So this is the basis, you can say, mathematical basis for thinking of turbulence as creating mixing, right? So that's what we usually think of, right? You have a turbulent flow field, you put some particles, you expect things to spread. And what we're getting here is that spreading is going to happen diffusively, just like Taylor diffusion that we talked about in the last class, with a diffusion coefficient given by the variance of the velocity fluctuations, right, which makes physical sense. And that's what engineers would argue intuitively, but here you can see one can prove that that will exactly be the behavior. Right? So a bunch of particles will exactly diffuse, provided the flow field you have can be replaced or can be approximated well as homogeneous, isotropic, and delta correlated in time. Okay. So any way in which you break this will mean that the effect of turbulence is not going to be simple diffusion. So for example, you look at, let's say, something mixing in the ocean, right? There will be some spreading, but it won't be featureless diffusion. It usually spreads in some meanders. You'll see patterns, right? You'll see vortex patterns and all kinds of things. If you look at plankton bloom in the ocean, they spread around, but they have all kinds of interesting shapes. It's not just spreading diffusively in a featureless way. So all those structures that one sees in turbulent mixing, which are departures from this simple diffusion, have the origin in the fact that the flow is not delta correlated. Right? That there are time correlations in the flow which are interacting with the scalar field somehow, right? And the fact that it need not be homogeneous and isotropic. So for example, if you look at mixing in a channel flow, it's not going to be so simple, right? Because there the flow is not homogeneous and it is not isotropic. The fluctuations in the direction of the channel will be much larger than transverse, for example. Or fluctuations near the wall will be much weaker than near the center. So all that will break this simple assumption. If it's isotropic, you can correct for homogeneity by making this a function of space. That is not too difficult. So then you will still have diffusion behavior, but which varies in space. So more diffusivity near the center line, less near the wall. More tricky is the isotropy part of it. But even beyond that, the moment you break those two things, we cannot interpret this equation on top in the Stratonovich sense anymore. Right? So that's even deeper than just changing the final equation. Right? Here itself, I won't be Stratonovich if my field is not homogeneous isotropic. So then the question is, what is the correct limit, and would that introduce more corrections? Okay. So doing this exercise now, which we are able to do at the end of this course, is not just to show, okay, that there is a mathematical basis for eddy diffusion. It also shows you how great an assumption one must make for that to really work. Right? The flow has to be homogeneous, isotropic, so that you can, and delta correlated in time. Or rather, other way around, delta correlated in time, plus homogeneous and isotropic, so you have the Stratonovich interpretation. Then that should be same as Ito incompressibility, and then that will give us this. So there's a lot of assumptions before you can expect eddy diffusion to work perfectly. Therefore, in any real situation, it's really very approximate, and in some cases, it can be very bad. Okay? But in the simple cases, it works, and we can see why. Okay, so in the end, if you see, the derivation was quite trivial, right? We just started with the equation dxi is dui, looked at the expectation for f, and did the same derivation as in Gardner to go from SDE to Foucault-Planck, and bang, we get the eddy diffusion. It is not even a 2-minute calculation. But to do this, we had to do many things, right? We had to understand, first of all, what that SDE means, then how to deal with the multiplicative noise, recognize that it is Stratonovich, which took us 5-6 lectures, right? Then convert Stratonovich to Ito, then use Ito calculus to get this expression for df, and then finally get this. Right? So we need the full machinery of this course to do in the end a 2-minute derivation. Okay, so just pause the recording. 1 second. Okay. Then you can edit it later. Okay, so what I'll do is I have just 5 minutes more to record. So if you all have to go for another class, you all can carry on. I'll finish the recording and you can catch up online. If you're free, then you can stay in the class. So we'll not carry on for very long, maybe another 10 minutes. Yeah, we'll just carry on the recording. That's okay. So it's still recording, right? Okay, so I'll carry on. You can edit this out. Okay, good. So now what we're going to do next is, so we've already seen that this Crichton field gives rise to diffusion. I want to now show this to you directly if we were to start with an advection diffusion equation for, let's say, a temperature field. Now we have seen it by looking at a tracer. So if we think about how is how are a collection of tracers or a single tracer going to behave in a flow, we've just through its Fokker-Planck equation for the distribution of the position of the tracer, or equivalently for the concentration of a bunch of tracers in a dilute system, we've seen that that has a diffusive behavior. So there we have derived Eddy diffusion in that way. But let's do it now directly for, let's say, a scalar field. One can also do this derivation of the effective mean scalar field equation through tracers by saying that basically when you have a scalar field, you're saying that the value of the scalar field on the tracer remains the same as it moves around. So from there you can use this tracer equation to get the scalar transport. But rather than do that, I would like to go directly to the scalar transport equation. And in the end, again, you'll see the derivation is very simple now that we have the basic ideas. Okay, so let's think about the scalar transport of some field theta. Okay, so theta could be concentration, it could be temperature, okay, or any other scalar field which would satisfy an advection equation. So I'm ignoring molecular diffusion. Just for simplicity, ignore molecular diffusion. Right? In that case, I would just have dou theta by dou t is equal to V I dou theta by dou xi, V dot grad theta. Moreover, I will say, right, ignore molecular diffusion and let's take the mean of the velocity field to be 0, just to emphasize the point. So remember, this is what I started with in the beginning of the course as the third interesting question. Right? So I said, let's have, I have a theta, it satisfies an advection equation because it is no molecular diffusion. And there's a velocity field Vi. Now, sorry, minus sign. Velocity field Vi. So if I'm saying the velocity field Vi is turbulent with 0 mean, and I take a simple average of this equation, correct? And I average both sides and assume these two things are independent, right? I'll get average of this, and if I say, oh, now I'm going to replace Vi by a random field, which I'm tossing some numbers, why should it be correlated? Let me say average of this is the product of the averages. When I do it, it will go to 0. And then we said something is wrong because that means that the rate of change of the average field, so I start with, let's say, hot temperature here, cold elsewhere, and it's a turbulent flow. I'll expect the temperature to become even after some time because turbulent mixes. But if I look at this equation and take the average of the field and look at it in time, average means ensemble average, right? So many different experiments, if I take their average and look in time, dTt of the average of theta will become 0 if I could take the average and split the average. So that's obviously wrong because it tells me that the temperature on average is not leaving. That means turbulence is not mixing. So that's when we recognized there was a problem with when we take the average here, I cannot split it because somehow these things are doing something in a correlated way, right, in the white noise limit. And now we know what the problem was, right? Because you can immediately see that if I now replace this with a Crichton field in the regularized fashion, right? So we use Crichton model. I would rewrite it as an SD for d theta is equal to blah 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 dt, and Vi dt will become my dui, right? And theta itself is a field, right? It's a function of x. And this thing now must be in the, so now I have a product. I can put circle to represent Stratonov. So the whole point is it must be Stratonov. So this is more explicitly multiplicative, right? Because earlier in the Lagrangian trajectory equation, the dui was multiplicative because the dui field was being evaluated at the position of the particle. Here that's not happening anymore. I only have x on the grid. There is no moving tracers. Right? I have theta specified on some fixed grid. I have dui specified on a fixed grid. And this is just a gradient of the theta. So this is some space-dependent field which is multiplying my vector, my field of noises. Therefore, this is an explicit multiplicative coefficient, right? Because this coefficient, of course, depends on theta. So this is in the most standard form. I can clearly see it is multiplicative. And this multiplicative product, because it has to be Stashnovich, I put the circle. And I know it has to be Stashnovich. Why? Because the properties of this noise decides whether it is Stashnovich or not. Same arguments, right? Because this field is isotropic, there will be symmetry on the indices, ij, I1 to 3. And because it's homogeneous, any two spatial positions can be interchanged. So the correlation matrix of all the noises in space and in velocity vectors will all be symmetric. So because of that symmetry, when I take the white noise limit, I will get Stashnovich. So I'll put a circle. Now all I have to do is go from Stashnovich to Ito and then take the average. Because if I take the average now, you'll immediately see, okay, average I can put here. When I put average here, it's average of a Stashnovich product. It is not 0. Right? Average of Ito is only 0. So therefore, the simple way to get the answer to this problem is to convert this to Ito. So this is Stashnovich, obviously. So now we convert to Ito. So we do exactly what we did before. You have minus so now this is going to be evaluated at the beginning of the interval, so it is just DUI. Right? I remove the circle. Right? And I'm now going to have dou by dou xi, so spatial gradient of the theta field at the midpoint. So that coefficient is just the divergence of the theta field. The question is when to take the theta field, right? In the Ito, the theta field is at the beginning, right? And now I have the theta field at the midpoint of its update. So theta plus d theta by 2 has to be taken divergence. And again, to get the Ito, you replace d theta again by this equation, but now with the Ito interpretation. This is just, of course, a shorthand, right? It's not a proof. But like I showed you in the beginning, if you start with that Stashnovich integral, you can show that it will amount to the same thing. So now that we have this theta, we replace theta by this thing, but now with the Ito interpretation. So we just, this term will stay as it is. Let's just look at this term. What did I do? Sorry, this is not there. Yeah, this, so this circle means I'm doing this at the midpoint. And now if I split this up, this is the Ito part, right, minus 1 by 2 dou by dou xi of d theta of d theta, right? 1 by 2 dui dou by dou xi of d theta, but d theta is this, right? Instead of I should use j. So this is the crucial step. Just let me know if there's any confusion. Okay, so this is just the definition, right, of the Stashnovich product, that I take the divergence not of theta at the starting point, but theta plus d theta by 2. Right? Now I do an expansion. So it's at the starting point and minus the derivative of d theta by 2, where d theta is replaced here. So then I have the derivative of this whole thing into dui. Now what I want to do, I want to bring together the product of dui, duj, so that I can replace it by the correlation tensor. Right? So when I do that, right, I can bring this guy inside, because again, in an incompressible flow field, d by dx I of dui is equal to 0. So this thing is the same as right? And now this thing is simply delta ij, the variance, right? D tilde at 0. And delta ij means I can equate these two things. So very nicely I get d theta is equal to minus dou theta by dou xi dui minus okay. So once again, I can take this in, right? I again get delta ij, and just like before, I get now a diffusion term, right? With the same eddy diffusivity. Okay, so the same eddy diffusivity we got from tracer motion comes out automatically when we take the scalar transport equation, right? And convert from Saturninus to Eto. Now, of course, I need to take the average, right? So now when I take the average, since I have the vector going to 0, this will drop out, and the only average that will survive is this term, because the dui will go off. So I will say, on average, my theta field will diffuse with the same eddy diffusivity, which is the variance, relative variance of the flow by 2. I made a, yes, I have a extra sign because when I replaced dt, I didn't keep the minus sign, right? So this dt by 2, when I put it here, I have a minus sign here. So I took d by dxi of theta with its minus sign, and then minus d by dxi by 2 came out, dui, but this d theta had to be replaced. D theta itself is minus. So there's a minus sign, that's why it became plus. Otherwise, I was worried about my sign, plus. So now when I take the average, right, I'll take average of this, which will split up, because this is Eto, right? This will go off, or it will be whatever the mean is, right? So if you decide to keep a mean flow, this will just become advection. If there's no mean flow, it will become 0. And this mean, I mean, this doesn't depend on the noise, it stays there. So now you can see that, and then I can now divide by dt. So I'll get d by dt of the average of theta is got an advection term, where this is like the velocity, mean velocity, and a diffusion term, right? Oh, sorry, when I replace this, I also have dt, right? dt. So dui, duj correlation is delta ij d tilde dt. So there's a dt here. If I divide throughout by tt, I'll get what looks like my usual PD, right? So ddt of the, maybe I'll write it down. So finally, I can say of the average is equal to, if you want, let me keep that, the mean of vi, which you can set to 0 if you want. On taking the average. Right, and so once again we see now this is what we were, this answers the third question of the course, right? That I start with this equation, standard advection equation. If you now put molecular diffusion, you will just get an extra diffusion term, right? It will change nothing. So if I start with just a pure advection equation and I have a turbulent velocity field and I want to understand the mean behavior, right, in a simple way, so I say let me model the velocity field by a random field. That's what we've done now. And then I take the average to find the mean behavior. The main point is it's Stratonovich, right? If you interpret it as Eto, you get the wrong result immediately. So right here, if I had said, oh, this product is Eto, it's obviously multiplicative, right? This is the noise field, which doesn't have any dependence on the dependent variable. the entire dependence on theta sits in the coefficient. It's multiplicative. If I interpret it in Ito and I take the average, I get the absurd result that the field on average, if it has some initial distribution, will not evolve. So the whole thing is it is not Ito, and we can say it is Stratonovich now confidently because this correlation of the noises in space and different components is symmetric. So for isotropic homogeneous Kryknen field, I can interpret it in the Stratonovich way, only for that, right? Then I can immediately do Stratonovich to Ito, use standard Ito calculus, and now take the mean, and beautifully we get that the evolution of the average theta field has the mean advection because of the average of the flow. If there is no average of the flow, this is 0. And I get the evolution of the mean field is simply a diffusion, right? With an eddy diffusion again, which is simply related directly to the variance of this field. Okay, so this is the result to which we have been going all along. And again, the derivation in the end, once we have all the tools, is quite simple to see, right? But it requires a lot of background. Okay, so this is brings us to, I would say, the conclusion of all the 3 questions of the course now. Right? We have seen how to understand the connection between continuum equations for concentration fields and SDs, right? Through the Foucault-Planck to SDE connection. Then that itself required us to fully understand the mathematical nature of SDs, and that showed us that there is different definitions, particularly Ito and Stratonovich. And then finally, we've been able to see why the Stratonovich works, and then apply these ideas to turbulence now and prove that at least for homogeneous isotropic turbulence, when you replace it with White and noise field, you can exactly get eddy diffusion. Okay. So if you're looking at homogeneous isotropic turbulence, its behavior will be pure diffusion provided it is delta correlated in time. Of course, that is not the case, right? So it's like saying if I'm going to model turbulence as just having diffusion, it's as good as saying my turbulence is really a White in time field, which is of course not the case, right? But that is the important point. So we know exactly, precisely what is the assumption we are making. And when it works, it basically means that what I'm looking at now, okay, so that also tells me when will this work. So I know it's going to work if it's delta correlated. So when is delta correlated a good assumption? If the time scale of fluctuations of the flow are much, much smaller than my observation time. Now I know that my turbulence has a whole range of time scales, and it's a continuum of time scales, like I showed you in the last class, right? The frequency distribution is a power law. So I can be 100% sure that it is a good approximation to be delta correlated if even the largest time scale of turbulence is going to be small compared to my observation time. This just means that I'm observing the field evolving on times much greater than capital T, the large eddy time. And that's when I said Taylor, right, already showed that you'll have Taylor dispersion, which is like just diffusion, where the diffusion coefficient is related to the variance of the flow. This is what we said from Kolmogorov phenomenology, because then if you're looking at the process at very long time scales, much greater than the largest eddy time scale in the flow, then it's like saying over these large length and time scales, all the individual eddies are uncorrelated. So all the eddies are basically giving you some kind of random motion on those long time scales. And so for the physical argument, you can say, okay, I'll get some kind of diffusion. And just dimensionally, diffusion must be meter square per second. So it's related to velocity square into some length of the large eddy. So the variance of the velocity is sitting there. This is what I told you in Taylor. That's Taylor's argument basically for saying that at very long times, turbulence will diffuse. And now, but that's identical to saying, to say it more precisely, you're saying that turbulent flow is basically White in time compared to my evolution timescales. So when you make that approximation rigorously, you can prove the diffusion, which earlier we were just saying heuristically, right? That if I have different eddies swirling around, they would on long timescales look like random walk. But now we have proved it. But the underlying assumption is identical, because when we say long timescale is much greater than large eddy turnover time, precisely we are saying the flow can be replaced by White in time noise. And that's exactly when we get analytically eddy diffusion. Okay, so with this, we'll come to the end of this lecture. Okay. Thank you.